Hello everyone, welcome to the second day of Math 262 Coronavirus Edition. Quick reminder, you have WebAssign due again on Friday, and after today you should know everything you need to know to do this WebAssign assignment. Another reminder, make sure you upload a copy of your notes each day where you watch the videos and take notes on them. Today will be the first time where you need to solve a couple problems, or at least attempt to solve a couple problems on your own when you upload it. You can take a picture of each of your pages of notes and upload those files, or whatever you want to do. So, quick reminder from last time, if you look back in your notes, you'll see that we learned about the direct comparison test and the limit comparison test last class. And today I'm going to go through a couple examples about knowing when you use each of these two types of tests. Sometimes it will be easy and sometimes it won't be quite so easy to tell. And then at the end, I'm going to give you a couple problems where you're going to determine whether this series converge or diverge. I will help you figure out what method to use, but you'll actually need to work it out. And the working it out part is what I will leave for you to do and upload as part of your assignment. All right, well, let's get started. So, let's take a look at the following. So, we're going to look at a series that's a little bit strange, and at first you might not know, does this converge or diverge? Now, this is an interesting series because you might not know what to compare it to. And so, there's nothing really to compare it to for a direct comparison test. So let's just take a look at another series that doesn't look that similar, but we know it diverges by the p-test. Okay, well, if these are the a(n) terms, and these are the b(n) terms on the right, we need to take a limit. Alright, well, we're going to replace this by a limit of functions. And what do we notice about the numerator and the denominator? Well, we notice about the denominator that it's clearly going to 0 as x goes to infinity, but so is the numerator. And so what rule do we use whenever the numerator and denominator are both going to 0? That's right, we use L'Hopital's rule. So for L'Hopital's rule, we need to take the derivative of the numerator and the denominator, and what we get is the cosine of 1 over x times negative 1 over x squared from the chain rule, and the denominator we just get negative 1 over x squared. We see that the negative 1 over x squareds cancel out, and therefore we're just left with the limit as x goes to infinity of the cosine of 1 over x. Now we see that 1 over x is going to 0, and therefore the cosine of x, or so the cosine of 1 over x, must be going to the cosine of 0, which is 1. That's the cosine of 0. What do we notice about this number? Well, it's positive and it's finite. Therefore, what this tells us is that the sum from n equals 1 to infinity of the sine of 1 over n diverges by the limit comparison test. All right. So, how else would we have figured that out? This is a really interesting problem because it combines your knowledge with series with your previous knowledge from L'Hopital's rule. So that's a great problem, but that's not the most typical of problems. I'm going to talk about an example as a refresher from last time, and then I will give you some problems. All right, let's do one more problem. and then I'll give you your problems to do. So let's take a look again at a sum that looks like the following. So this is the sum of n over n squared plus 1 squared. Now you could do this by the integral test, but it's far easier to do it with limit comparison, I believe. There's fewer things to verify. So you get n over n to the fourth plus 2n squared plus 1. Alright, now what should we compare this with? Well, this is a great problem, is figuring out what do we compare it with since it is a rational function. So I want you to pause the video now and attempt to do this one. Figure out what series goes on the right without me telling you. Alright, go ahead and pause the video and figure that out. Now that you've had to do that, you've had the chance to do that, we notice that we see the biggest term on top is n to the 1, and the biggest term on bottom is an n to the fourth. Therefore, our series we're going to compare it to is n over n to the fourth. Or in other words, that's the same as the sum of 1 over n cubed. This is a general pattern with rational functions. You take the biggest power of n in the numerator and the biggest power of n in the denominator, and you divide them, and that's what gives you the series you're going to compare with. Well, we see this clearly converges by the p-test with p equal to 3, which is bigger than 1. And now we need to do the limit comparison test. Well, these are the bn values, and these are the an values, and so we need to take a limit as n goes to infinity of an over bn. And what we get is the following. It's very important to make sure that when you divide fractions, you get it all right in the end. Remember, when you divide by a fraction, it's the same as multiplying by its reciprocal. And then we need to take the limit of this lovely expression. Well, what we notice is that the degree of the numerator is 4, and the degree of the denominator is 4. Therefore, the limit is the ratio of the leading terms. They're both 1. Therefore, the limit is 1, which is bigger than 0. And what this tells us is we know that our series is going to converge by the limit comparison test, because the series we compared it with also converged. All right, very good. So we've seen a lot of series where we use comparison and direct comparison tests, limit comparison and direct comparison. We often use the limit comparison. We use it more than we use the direct comparison, but I'm going to give you some examples, and these examples might involve any of the series tests we've done so far. They could be telescoping, they could be geometric, they could be p-series, and so I'm going to list them, and then I want you to pause the video and identify the method you're going to use to calculate whether they converge or diverge. And if they converge, you can maybe calculate the sum in an instance or two. So let's list the possibilities. So we have the sum from n equals 1 to infinity of the cube root of n over n. We have the sum from 1 to infinity of 1 over 5 to the n plus 1. We have the sum from n equals 3 to infinity of 1 over n cubed minus 8. We have the sum from n equals 1 to infinity of 1 over n plus 1 minus 1 over n plus 2. Okay, so I want you to pause the video and identify what method are we going to use. Are they going to be direct comparison, limit comparison, p-series? Are they going to be telescoping, geometric? So pause the video, take a few minutes to identify it, and go ahead and show whether these series converge or diverge. In a few minutes, I'm going to identify one method to figure out whether they converge or diverge, and then the work to actually show that is up to you. So go ahead and pause the video for a minute and figure these out. Now that you've had that chance, this first one is actually a p-series because you can simplify the fraction right there. And I will let you do that. You can also do a direct comparison if you want, that's fine too. But a p-series or a direct comparison are the way to go. The second one is a direct comparison, and I'll let you figure out what to compare it with. The next one is a limit comparison. And the last one is a telescoping series. Be sure when you work on these notes to figure out how do we know that these series work? And in the case of the telescoping series, what does it converge to? Last but not least, I'm going to give you one more example. And this one is the sum from n equals 1 to infinity of 5 times negative 4/3 to the n. And I probably don't need to tell you that this is a geometric series. So I wanted you to get some practice identifying what method to use, so make sure that you've done the work to get credit for your notes with showing that these converge or diverge. If it's a geometric series, identify the ratio. If it's a telescoping series, identify what the sum is of the whole series. If it's limit comparison, see what it compares to, and then do the limit that you need to do to show that your series converges or diverges. All right, well, that's all I've got for today. We'll have a new section to start on Wednesday, but if you have any questions, please email me or post your questions in the thread online. I hope you take care, and I will hopefully see you all soon.